Welcome back. Today we will discuss catalytic cyclobutene formation reaction. We started the reaction in the last class. After catalytic cyclobutene formation, we will then move on to cyclopropane alcohol synthesis, cyclopropanol synthesis, Kulinkovich reaction, that is another very beautiful reaction to form the cyclobutane along with it an alcohol or an amine. Subsequently, we will discuss the Poisson-Khond reaction and briefly we will discuss the mechanism in this class. First then cyclobutene formation and then cyclohexane hydroxide synthesis or cyclohexane amine synthesis. Subsequently, we will move on to the cyclopentenone synthesis by Poisson-Khond reaction. Let us look at the catalytic cyclobutene formation. So, the reagent as we were mentioning in the last class that is required for this reaction is alkynyl halide. Alkynyl halide will react with dicyclopentadienyl zirconium, for example. Dichloride, you need a Grignard reagent to get the dicyclopentadienyl zirconium reagent from it, that is why the ethyl magnesium bromide you need ideally that what is used over here is 3 equivalent THF room temperature and 10 mole% of this gives rise to the cyclobutene species from this reaction. And you can have the variation of it, for example, if you have cyclobutane chloride along with an olefin, still selectively olefins will react with it to give rise to the desired cyclobutene product without touching the olefin that is associated with this starting material. So, these species will remain unreacted from this synthesis, and this is reported by Takahashi Chemcom 1998-1989. Okay. So, that is the page number. So, it is a catalytic cyclobutene formation reaction which is beautifully done by starting from alkynyl halide by reacting with dicyclopentadienyl zirconium unsaturated compound. How did you synthesize dicyclopentadienyl zirconium unsaturated compound? That is by starting with the zirconium dichloride species and reacting with the Grignard reagent, such as over here we have taken ethyl magnesium bromide for this purpose. Let us look at the mechanism of this, which involves the oxidative cyclization reaction as one would imagine. Let us look at the mechanism of it. Overall, we will have the mechanism of the cyclobutene formation. We in the process, of course, dicyclopentadiene zirconium, the cyclopropane ring will be formed. This is the ethyl magnesium bromide partner that is generating this intermediate. We have, let us say, R alkynyl chloride, and we will get a 5-membered intermediate where dicyclopentadiene zirconium is part of the ring. Overall, we then have R and chloride over there, and this is the one, this ethyl. So, it is a oxidative cyclization between this olefin and the alkyne. Overall, we will then get a 5-membered intermediate. From there on, this 4-membered ring formation happens and zirconium goes out with the help of ethyl magnesium bromide, right. We do need a cyclopropane ring formation, that is the ring formation between this carbon and that carbon, and then overall from there on the zirconium chloride and Cp2 reacts and stage with it, and finally we do have ethyl magnesium bromide that is used for the reaction. Participating in this, again MgBrCl will go out, zirconium alkyl intermediate coming into the picture, and from there on we will see that beta abstraction will take place overall to give rise to the final product by beta abstraction to give the cyclopentadienyl zirconium 3-membered ring along with the cyclobutene formation. So, this part will give you the cyclobutene formation. So, this mechanism is as expected on a simpler note, where cyclopentadienyl zirconium reagent is giving you the 3-membered metallocycle species that is originated from ethyl magnesium bromide, which then react with alkynyl halide to give rise to the 5-membered intermediate. Rearrangement from there on gives to the intermediate, where zirconium chloride and cyclopentadienyl is a substituent on the cyclobutene ring that is just formed, and from there on another equivalent of ethyl magnesium bromide will give to the alkyl substituent on the zirconium, where chloride is going out. From there on beta abstraction will give rise to the cyclobutene formation, and overall you will get back the zirconium this 3-membered intermediate zirconium metallocycle intermediate, which then can be recycled for the catalytic cycle. So, this is a very simplified mechanism for a cyclobutene formation, which is otherwise very difficult to synthesize by other technique from a readily available starting material. So, this simple cyclobutene formation then leads to the variety of product formation, where even if you have other olefin associated with the cyclobutene ring, still those can be tolerated under the reaction condition, which is quite remarkable for oxidative cyclization reaction. Then we will discuss Kulinkovich reaction, okay, which is the cyclopropane alcohol synthesis or cyclopropane amine synthesis from a suitable starting material. Let us look at how the cyclopropane alcohol or cyclopropane amine can be synthesized even from the simplest starting material, for example, ethyl acetate or any ketone, and combination any ester or amide in combination with the suitable olefin can give rise to the cyclopropane ring along with that hydroxo or amine substituent on it. So, let us look at Kulinkovich reaction, and after this we will be looking at the Poisson-Count reaction. So, Kulinkovich reaction. Okay, it is as I mentioned, it is a reaction of an ester and titanium tetraisopropoxide, right, with 2 equivalent of ethyl magnesium bromide that will give rise to the cyclopropane ring with titanosin intermediate will be formed, and overall you will get the cyclopropanol, where this part is reacting with the titanosin reagent to give the cyclopropanol. A variety of different versions are known, both stoichiometric and catalytic versions are known. If you are taking an NR2 over here amide, you can have an amine substituted cyclopropane, in this case methyl titanium isopropoxide was taken as the reagent, and for example isopropoxide again was taken, and if you are taking R2 and R3 as the reagent, from this we will have cyclopropane ring formation with amine substituent with it. For example, over here we can have substituent coming from different substituent coming from the alkyl Grignard reagent. So, this reaction, Kulinkovich reaction, is a powerful technique for synthesizing the cyclopropane ring with alcohol or amine substituent on it. The first formation will be the titanosin intermediate, where 3-membered titanium intermediate will be formed starting with a Grignard reagent. If you, for example, it is a cyclopropane ring formation with titanium in it for the ethyl magnesium bromide, or any other Grignard reagent with substituent at the alpha carbon or beta carbon without any problem can be tolerated, and these 3-membered titanosin intermediate then can react with ester or amide to give the alcohol or amine substitution on the cyclopropane ring. Let us look at the mechanism of it, which is, as you can expect, is quite simple by involving the titanium cyclopropane ring formation reactions. Let us look at the mechanism of it. Okay. So, the mechanism as you would expect, the first step as before, it is isopropoxide for reacting with ethyl magnesium bromide to give titanium dialkyl intermediate. If you want to go through it, RO2. From there on, a beta abstraction will set to the ethane, okay, and the titanosin intermediate, where different RO group can be reacted. From there on, for example, the ester, if we are talking, ester can be reacted to give rise to the coordination first of the ester with the titanium intermediate with cyclopropane ring on it, and overall then this intermediate can react with the RO minus, that alkoxide that we were using for the titanium. This alkoxide can react or attack the titanium to make it RO3 minus and a 5-membered. So, now oxidative cyclization between this 3-membered metallocycle and the ketone will take place to give the overall 5-membered intermediate, giving rise to a species where this ester is attacked by this cyclopropane ring, and finally, this will then move on to give you overall this intermediate, from where formation of the cyclopropane ring can be envisioned very easily. So, this is the intermediate where the cyclopropane ring will be forming. Of course, this lone pair can be coordinated with it. We have OR3 along with it and R prime. From here, the product formation can be envisioned. So, overall, as you can see, it is a titanosin intermediate formation with a 3-membered cyclopropane like intermediate that is reacting with the ester, where ester is first coordinated with this titanosin intermediate, and then oxidative cyclization gives rise to the 5-membered intermediate, which upon rearrangement, of course, the ester leaving group OR will go out upon rearrangement, and it can ring close to give to the cyclopropane with substituted with the alcohol substituent, as one would see quite easily. Now, this Kulinkovich reaction not only can be reactive with various these Grignard reagent partner that can be envisioned. Of course, if the cyclometallotitanosin reagent can be exchanged with another olefin, that for example, styrene, if we are interested in bringing in the styrene can be reacted with for example, ethyl acetate or any suitable ester to give rise to the cyclopropane ring. So, the 2 carbons will be coming from styrene double bond, and another carbonyl center carbon will be forming the 3-membered cyclopropane ring from there, and we can also get the corresponding alcohol. So, cyclopropanol synthesis can be simplified by this Kulinkovich reaction, which is a very powerful technique for synthesizing such compound. Let us look at the styrene example, where we will see that styrene is participating in these reactions. So, we will be discussing the example with styrene and ethyl acetate. Kulinkovich reaction continuing, ethyl acetate is reacting with styrene to give rise to the, of course, the reaction condition is similar as we have discussed. Ethyl magnesium bromide, titanium isopropoxide, 10 mole% overall from this Kulinkovich reaction we get an intermediate where we have cyclobutene formation from this, and methyl is coming from the ethyl acetate, that methyl, and this hydroxy in 42% yield. Now, this is again starting from a titanium cyclopropane like intermediate. Okay. We can then swap with the styrene. This olefin can be swapped with the styrene. Overall, then we will have dialkoxide titanium, the cyclopropane intermediate, where this phenyl is associated with it. Subsequently, we can have ethyl acetate, for example, over here will interact with titanium, will interact with this first, and during the process it will generate the chiral center as one of the diastereomer that would be generated over here, and this will be up, and we can have the OR diisopropoxide intermediate. From there on, another alkoxide will be attacking the titanium overall to give the RO3 minus just like before, and during the cyclization this step, that step will proceed with the retention of configuration at the migrating carbon. So, this carbon center during cyclization when it migrates over there, so this will go out and this member will coming in during this migration. It occurs with retention of configuration. That is quite interesting. So, overall you will see that these diastereomers formations are quite interestingly set up by this Kulinkovich reaction published in EJOC 2004. So, 2004 EJOC 4517 is the page number. This is again a beautiful reaction, Kulinkovich reaction, where we have seen styrene can be participated, for example, also with ethyl acetate. CH3CO acyl part is participating into the cyclopropane ring formation with this styrene intermediate, where styrene reacting with the acetyl part to give the cyclopropane ring, and cyclopropanol formation is happening with retention of configuration at the key bond making step that we were discussing. So, the mechanism for these reactions are very simple. Oxidative cyclization is at the core of these processes, where we have seen that metal oxidation state goes up by +2 during the oxidative process, and then cyclization kicks in, wherein we do see that the interesting product can be generated by this technique. Well, now we will move to the next example of this oxidative cyclization process, where olefin and alkyne along with carbon monoxide can be participating and giving rise to the beautiful cyclopentanone product formation. These are the name reaction and very famous reaction known as Poisson-Khondt reaction, where olefin and alkyne is participating with carbon monoxide overall to give the 5-membered cyclopentanone formation quite efficiently. The mechanism of these reactions are quite simple, but it is quite attractive as well, and the application of these reactions are far reaching, and many natural product synthesis has been utilizing this technique or this strategy beautifully over the years or decades, I would say. Now, let us look at the Poisson-Khondt reaction, where 3-membered intermediate or 3-membered reagents or 3 reagents are participating in the cobalt site to form the final product. Okay. Poisson-Khondt reaction. So, Poisson-Khondt reaction is one of the very widely studied reaction. Okay. Poisson-Khondt reaction, usually it is an olefin substituted, of course, and an alkyne. Again, it can have small group and a big group, this is big and this is small. Overall you will see that reacting with dicobalt center CO2CO8 and giving rise to the cyclobutanone product, where big substituent is near the ketone site and the small substituent on the far from the ketone, and the R can be at alpha or the beta position. Usually acetylene and terminal alkynes works best. Okay. That is from the alkyne part. Acetylene and terminal alkyne works best. It is very sensitive to alkene substituent. The type of substituent will control the reaction quite a lot. In general, tri and tetra substituted alkenes really do not work that very well. Excellent functional group compatibility is seen for this reaction, and most commonly it is performed with stoichiometric amount of this dicobalto CO2CO8. There are, however, many instances where we have seen the use of alkyne complex, that is CO2CO6 alkyne complex. So, this as you see is a very powerful technique for formation of cyclobutanone, right, cyclopentanone. Cyclopentanone synthesis can be always very simplified, and whenever a cyclopentanone ring is there or any advanced analog is there, that is usually trusted with this natural product synthesis for utilizing this Poisson-Khon reaction. It is a reaction between an olefin and an alkyne along with a carbon monoxide to give the 5-membered cyclopentanone reaction intermediate. Now, as you have seen, olefin can be of different substitution pattern. However, tetra substituted olefin or tri substituted olefins are usually problematic for these cases. It works beautifully for alkynes which are terminal in nature or acetylenic in nature. Otherwise, functional group tolerance is quite high for these reactions, and that is a very good news. Usually stoichiometric amount of CO2CO8 is used for this reaction. Dicobalto octacarbonyl species are used, but sometimes it is also CO2CO6 alkyne species are used for these processes. Let us look at the mechanism of these processes, how olefin and alkyne is put together along with carbon monoxide to give the 5-membered these organic intermediate, which are cyclopentanone in nature, and we will see the subsequent application of this method in the next classes. Okay. So, Poisson-Khon reaction mechanism we are going to discuss. PK reaction, let us say Poisson-Khon reaction. Now, usually as I was telling, it is the although it has excellent functional group compatibility, it is very sensitive to alkene substitution. In general, tri and tetra substituted alkenes do not work that very well. Acetylene and terminal alkynes are the best one. Let us therefore take the terminal alkyne. One of the terminal alkyne is reacted with the starting material, which is used usually in stoichiometric fashion. We can have CO, CO3 and another cobalt CO3 reagent in another center. Overall, we can have this alkyne incorporated interacting with the dicobalt center as is shown, and this is both the cobalt centers are interacting with both the carbon centers. So, this cobalt center interacting with this carbon center, this cobalt center is also interacting with this carbon center. There is a bond between them, and this cobalt also interacting with that one, this cobalt also interacting with that one. This is the insertion that controls the regiochemistry, the insertion that we will see right now, where one of the carbon monoxide will go out from, let us say, one of these processes, usually the one where the substituent is far from it. So, this carbon center is attached with both the center, but the substituent which are having both the carbonyl in tris carbonyl species, one of the unsaturation is created by leaving the CO, and the insertion is controlling the regiochemistry over here. We will see the insertion of olefin. Let us take in olefin here. Insertion of olefin will take place in a moment, where CO3 and R, that this R is coming from the alkyne, and this carbon center is associated with it. This insertion is occurring over here. This is the R prime, this is R prime olefin that is interacting over there. We have taken this dicobalto species for this reaction, and overall this is the intermediate where insertion is happening, and insertion of the olefin over here gives rise to this intermediate, from which alkyl migration and reductive elimination will give rise to the product formation. We will draw in the next page. So, what we have seen in this reaction mechanism is alkyne reacting with the dicobalto reagent to give rise to the intermediate, which is very efficiently giving rise to the alkyl migration, which is controlled by which is the center where regiochemistry is controlled. From where on we will see how the subsequent reactions are going by migration and reductive elimination processes. So, from that intermediate, let us try to draw the alkyl migration. From that previous intermediate, alkyl migration happens, and it gives rise to the very beautiful intermediate that is leading to the product formation. It is already looking like product now. That is great news, and from there on we will see that subsequent reductive elimination will lead to the product formation. Here reductive elimination and will lead to the, we need 2 equivalent of CO. Of course, reductive elimination in this step will lead to an intermediate where monocobalt intermediate is inserted into the ring, and overall this species then forms subsequently to give the product, final product. So, this is then can taken to the cyclobutene product formation that is involved into the process. So, from here CO2, CO7 will go out. In this case, what we have in particular seen that an alkyne, terminal alkynes in particular we have taken, terminal alkyne first reacted with this dicobalt center to form the intermediate, which then can incorporate the olefin, which insert regioselectively, and that is the olefin insertion is the regioselective step. From there on, alkyl migration onto one of the CO with cobalt species happens, and then subsequent reductive elimination closes the ring to give you the cyclopentanone intermediate. During this process, of course, cobalt CO2 CO7 goes out from the species. Overall, then this process is quite powerful in putting olefin and alkyne together, although all the substituent on the olefin and alkyne cannot be tolerated, but quite a wide variety of disubstituted olefin, monosubstituted olefin can be taken along with the alkyne, which are limited by the acetylene or a terminal alkyne mainly. These are the ones which is incorporated along with the carbon monoxide to give rise to the cyclopentanone intermediate. So, the steps involved is the incorporation of alkyne, then the migratory insertion of the olefin into the resulting intermediate. From there on, the alkyl migration into the carbon monoxide of the one which is associated with the cobalt, and from there on reductive elimination closes the ring to give the final product. So, with this we will conclude today's class. In the next class we will continue discussing the Poisson-Cohn reaction and some application of this. Please do keep studying this new reaction, that Kulinkovich reaction, Poisson-Cohn reaction, and also cyclobutene ring formation that we have discussed today. Till then, bye bye.